Hello and welcome everyone. Let's solve the same tree problem. This is also a binary tree problem. We started solving binary trees for some consecutive days now, so you might do well to check out the playlist and catch up with previously missed videos. The way the questions are structured is that a knowledge of or the prior knowledge of one of them is going to serve as a building block for easily solving the other problem. For instance, if you've seen the previous video, you would know that when manipulating data in a binary tree, we use the tree traversal method called BFS, binary first search, and DFS, depth first search, where we talked about how binary first search is a level order traversal and depth first search is a pre-order traversal that goes in depth through one part before branching out to other parts. Basically, if you don't understand what I'm talking about, then you might need to catch up on these terms, and I would recommend the previous video. Alright, so in this problem, we are given the root of two binary trees, and we want to write a function to check if they are the same or not. Binary trees are considered the same if they are structurally identical and the nodes have the same value. So this is obviously the same binary tree because we can see at first glance that they are structurally identical and the nodes have the same value. If, for instance, this had a value of 3 and this was a value of 2, they are structurally identical, but the nodes do not have the same value, in which case they would not be the same tree and would have to return false. So now let's make a basic rundown of how we might solve this problem. I always say this in binary tree problems, that one of the most important decisions you might have to make when you come across a binary tree problem is determining what traversal is much more appropriate for the problem. Now, in terms of time and space complexity, they would essentially result in the same time and space complexity. They run in a linear time because most likely you'd have to traverse as much as the given height or given input of the tree, and they always use extra space complexity. Breadth first search uses the queue data structure, first in first out, while the first search uses the stack data structure, last in first out. So essentially they are both using the same data structure and extra space, not the same data structure, but they're using extra data structure, extra space, and so the space complexity is also going to be linear. But some questions you might find might be easier to just solve using one or the other, but again, it's really up to you and you might choose to use whichever if you're so comfortable with it. This is one of those questions where it really doesn't matter. We can decide to traverse the values in order. Now, how are we going to compare? First, we are going to compare the roots. We are giving the root of the element, and at first we are going to compare the roots. If the roots are not the same, there is no need wasting our time traversing the entire tree because the root is not the same. There is no way they are going to be the same, right? So now that we've dealt with the root and we can see that okay, the root passes the vibe check and they are the same, we'll move on to the children node, and we can see from this example given that we have both the left child node and the right child node. So after the root, right, we want to compare the two children. Is the left node for the p the same as the left node for the q, the left child of the p, and is the right node for the p node the same as the right child for the q node? Basically, that is what we want to compare. We start from the root and we go back down. And like I mentioned earlier, we are going to be using both traversal, breadth first search, and depth first search. So we can choose to go in order and go from order comparing the nodes and the values, or we can choose to go depth first and we just pick one side and then visit the other side. It really doesn't matter, both works fine. And the time complexity is not going to be O of n in this case because we have two trees. We are going to have O of P plus Q. Basically, we have two separate inputs and our function is going to run as large as a combination of both input sizes, and this is also going to be the same case for our space complexity. Now let's jump right into the code. Alright, let's write some Python code, and we will start with the iterative breadth first search traversal. So first I'm going to define the queue data structure, and I'm going to be storing the nodes in a tuple. If you don't have this tuple data structure available to you in your programming language of choice, you can use a list like I will be using in the JavaScript code. While our queue is non-empty, I want to first get the values of both nodes, and popping basically removes the last element in the queue. But because a queue data structure is first in first out, we are supposed to remove the first element. So I'm going to be adding a 0 to it. But if you are writing DSA in Python, you can use the dec data structure. It is an inbuilt data structure that supports queue, so you just use pop left and it will just remove the first item. You don't need to use the 0. But I wanted to use a list for those that might not have that particular data structure available to them in their programming language of choice. In my videos, I would regularly switch between using a dec data structure and just showing you how you might go about it in your programming language of choice. Alright, so first we want to check if both nodes, right, if they are empty, then we can just continue because we are in a loop. And if one of them is empty, the other is not, then we want to return a false. Then want to return a false. Then want to make one last check. And what are we going to be checking? We want to check that the values are the same, but instead I'm going to be checking if they are not the same. I'm going to be returning a false immediately and just exit that code. Then lastly, we're going to traverse each children, right? So now this code, we're checking the root of the tree. Now after checking the roots, what do we want to do? If the roots are the same, they satisfy all of the condition, then want to check that the children are also the same. So we're going to append the left child and the right child to the node. So we can just go and check the left child of the node, of both nodes. And also don't forget that you are using the double brackets because this is a tuple. We are appending as a tuple. If you are using a list, don't forget your square brackets. And want to make the node 2 right, want to compare the right children, and if they are not the same, this condition is going to return false and exit the code immediately. But if they are, we want to go ahead and also return a true. So let's submit our code and see what we get. Okay, so we have this error, and basically it's saying that then our output is true whereas it should be false. So let's look at our code and see what we might be doing wrong. Silly mistake. So we are checking if node2.write and if node2.write, whereas it should be node1.write. And I'm just going to do a quick check and make sure that there is no other silly mistakes such as this. So let's try to submit it again. And we get a server error, an internal error. I'm not sure what is causing this, so I'm just going to try to submit again. And this works fine as it should. Alright, so let's try to make this a depth first search. Let's try the recursive solution. And one dead giveaway that recursive solution is going to work is because we are moving down a singular path. If you recall with depth first search, we want to traverse down a path, and as you can see here, we are traversing down the left node, traversing down the right node. This is an indication that we can call the same function on this code, right? Like instead of appending to the queue, we can call the function on this code. So let's try to eliminate the queue. We don't need a queue in a depth first search, we don't need a queue, and since queue doesn't exist anymore, then this wouldn't need to exist. This wouldn't need to exist because our queue does not exist anymore. We are not popping anything off. So I'm just going to define node 1 and node 2. Since we do not have it, we have P and Q, so I'm just going to define node 1 and node 2. And yeah, we cannot use continue because we are not in a loop, so instead we're just going to return a true. And also we are going to check that if one of them is not corresponding with the other, that is, if one is empty and the other one is not empty, we're just going to return a false immediately. And we can also add another if statement to check if the values are not the same, right? If they are not the same, also return false. And now we said we want to call is same tree, want to call the function on both nodes, and let's remove this indent. We don't need that indent, this is inaccurate. And we also don't need, my spelling of true is wrong, we also don't need this return because basically everything is running concurrently. We don't need that return. And this is not going to be a tuple anymore, this is going to be a regular function, like we can see with the a regular function. We're basically mimicking the parameters, and we should add self. If we don't want to add self to the argument, we can just add self like this. And so okay, we already have the function calling itself. What do we expect that it returns? So we know that, okay, similar to what it is returning, it's returning a boolean, right? It's just like we're calling this function on itself again, but for one part of the tree, and we know that it's going to return a boolean. But let us not forget that we also want to compare this same tree. Now I'm not even spelling the tree correctly, tree and tree. We want to compare the left tree and the right tree, that they are the same, and so we need to do this. And so we can just compare that they are both the same and give this a spin. Basically, we are calling this function on itself, and it will run as long as either of this condition is true or false. Now this is our depth first search. Again, our time complexity is O of P plus Q because the time race is going to be as long as both nodes, and our space complexity is also going to be O of P plus Q. For our breadth first search, we are obviously using a different data structure, but for our depth first search, we're using the recursion, which under the hood uses the call stack. Alright, now let's try to write some JavaScript code. So the breadth first search, first we are going to define the queue data structure, and it's going to be similar to what we had with the Python, but we're not using tuple, we'll be using a list of lists. And while queue dot length, we want to first extract we can call it node 1 or node 2, but since JavaScript is block scoped, this is going to be fine. Then we can just get the first values in our queue using the shift is going to get the first value, and we can just check that if P and Q are empty, then we want to continue our loop. If one of them is empty, then we know that this is not the same thing, and we want to return a false because they both should be empty. And we also want to check that their values are the same, but if they are not, this false should be lowercase because we are in JavaScript. We also want to return a false, but if either of those conditions are true, if P and Q, then we want to traverse down their children. If P and Q want to traverse down their children by pushing, not appending this time. Want to push the left child, that's going to be P dot left and Q dot left, and we also want to push Q dot P dot right, the right child this time, and Q dot right, and then we want to return true if all of this condition is satisfied. Basically, if it's false, it would have cut it here, and true is supposed to be in lowercase. All right, let's submit that. We have a false, and where is our false coming from? So we have P dot left, we have Q dot left, We have p.right, we have q.right. Okay, this is wrong. If p.val is not equal to q.val, that was a syntax error, pardon me. Alright, cool. Now let's try to make this a depth first search. First, we know that we need to get rid of our q. We don't need our q, and since our q doesn't exist anymore, our while loop doesn't need to exist. We don't need to remove and shift. We don't need to continue again, because we can just return that it is a true. Our continue only works because we are in a loop and we want to continue the loop, but we're not in any loop and we can just exit our loop. This doesn't need to exist anymore. This return true doesn't need to exist anymore, and we can just, like what we did with our Python code, compare is same tree. Again, this also doesn't need to exist really, because we are just going to be returning is same tree, and we do not need to use, we don't need to store our values in a list anymore. We can just return as is, and recall that we are returning. We want to return if they are the same, because basically if we are running a traversal down this tree, then it's meeting one of these conditions. True in lower is meeting one of these conditions, is either true or is returning false. But we also want to check that the left and the right are the same thing, right? And we just want to return if they are both the same thing. As you can see, this works fine, albeit a bit slower than the breadth first search, but I hope this was helpful, and I will see you in the next video. Thank you for watching.